This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
Today's topic, mechanically fastened joints. I'm going to take an approach, a couple different approaches here to look at these types of problems in bolted joint finite element modeling. Many structural analysis requirements address these assemblies and mechanically fastened joints, and finite element analysis certainly provides insight both into the detailed stresses of the assembly and into the load transfer mechanisms through the various parts. There's various, what I'd like to cover today is different bolted connection approaches for various levels of detail or analysis focus or requirements. And these two approaches, one will be a global level shell and beam modeling procedure, and another will be a detailed solid part connection problem. We're going to take a look at a few other items in more detail, and that includes applying bolt pretension, bolt and part contact and interaction between the various parts in the assembly, and also some topics with rigid body motion that often occurs in these types of problems, and try to help those issues in setting up your problem. And then with both types of problems, we'll look at post-processing important results quantities. This particular webinar is also a complement of the assembly modeling webinar that Peter Barrett has provided. That's available via our website. That particular webinar goes into some additional insight into contact setup and assembly modeling. So that's a nice complement to this webinar. The first modeling approach will take a look at a global level 2D plate and shell model with looking at basically 3D stress analysis. These particular models are primarily shell and beam construction. We may be after some general load transfer. We may be after some detailed stresses within parts. The holes may or may not be modeled discretely, and we want to connect all these different parts together, typically with beams and possibly constraint equations. So this is more of I would say, a global level modeling approach. You can see in this example problem down below, I have an example steel lug fitting attached to a couple aluminum angles and some fasteners, total of 8 fasteners going through these parts. And so this is just an idealized joint just to study for in this webinar and look at our contact setup and problem setup. These types of shell and beam modeling, you may be after stresses in the parts, but a lot of times the contact between these parts is not known ahead of time. The connections are idealized in the holes and the joints and modeled with beams and some form of attachment. So let's take a look at this. We're going to do most of the webinar today interactively through Workbench. And so if I take a look at the problem set up in this particular example, I've got my CAD part up. I've sliced up my surface bodies, which will be meshed with shell bodies, and I've got some holes discretely modeled. So if I take this modeling approach with shells and beams, I have a couple of different ways to attach these in mechanical or in the finite element analysis tool. Looking here at the geometry, I just wanted to describe a couple methods we're going to cover. First, one method is actually utilizing beam elements to attach the parts together, and the rest I'll utilize joints in the mechanical system. If you do have a line body within mechanical, shown in the outline tree as a line body, this will transfer over to mechanical, be meshed with beam elements, and we can generate those attachments. Using line bodies and beams are handy in this type of modeling procedure because you can assign a cross-section in Design Modeler and have that flow through to Mechanical to automatically assign the section properties to the beam elements. In this case, I've got one cross-section. This is available via the Concept menu, and you can assign various cross-sections to the beam elements that get generated. And in this section, I've got a circular cross-section defined as a particular number 6 high lock that I'll be using those titanium high locks to attach all the parts. And then once that is assigned to the line body, you can see down here that my circular cross-section here is assigned to that line body that will flow through to the mechanical tool and assign the appropriate properties. Let's switch back over now to the mechanical tool, and what we'll do is go through a little bit of the pre-processing here. I'll describe the pre-processing in mechanical and then go through some results of a solved problem. In here in the geometry setup, you could see that here's our line body with the beam model. We can assign the material directly to the beam models. There's our titanium alloy. You can see those are that is modeled as a single, or that is shown here as a single line element. And you can see with the mesh, if we highlight mesh, that'll display the mesh as a single beam element. Let me back up a little bit and show you some visualization tools for our geometry once it's brought in. In these 2D types of problems, we have to assign thicknesses and materials, sometimes under the geometry item here. If you go down into the details, you can assign the display of each body by a particular material, which is handy to confirm material assignment. You can see my structural steel lug with a couple aluminum alloy angles, and I've got a titanium alloy assigned to that beam element. You can also color code our geometry via shell thickness. So if there's various shell thicknesses, you can confirm that through the model, and these will be the shell thicknesses assigned to the shell finite elements. Some additional visualization tools from the View menu. You can, let me switch this back over to Material. I like the color coding there. Some additional visualization tools is you can look at thick shells and beams, and you can visualize cross-section solids. So those line bodies with that cross-section, you could see now, if we zoom in real close, that line body now is visualized at that actual cross-sectional diameter. So you can visualize that and confirm your fasteners in the right spot in the right diameter. Also, you can click on the mesh, and with visualizing thick shells and beams, it displays the shell elements at their true thickness just to kind of confirm the part fit up, if you will. Okay, that's just some visualization tools for confirming some pre-processing. Let's move down to, let me turn off the thick shells and beams here, and let's move down to our connections. Once we have a meshed finite element model, we now have to attach these bodies together. A couple different ways I want to demonstrate attaching these is attaching that beam element to both of our parts, and then also using a connection tool called a body-to-body joint. First, let's take a look at our beam here and make sure we can connect our beam here. With this existing beam, we're modeling that beam cross-section. We then have to connect the two ends of the beam to our various shell elements. And we can do that in our connection group, our joint folder, and we can go through the body-to-body and create a fixed joint. And that'll connect these two bodies. Let me turn off the cross-section solid so we can see that line body. What I've done is I've connected one end of the beam element to the model, and to show you how this works, you can create a fixed joint, and with the fixed joint, let me tie in the opposite end of the beam to our lug hole. We can zoom in here, we could see the end of that beam, and we're going to scope. We're going to switch over to a vertex selection. We'll select the reference to the end of that beam, and then connect the mobile to switch that over to the edge of our lug fitting. And when it does that, it creates a local coordinate system. It creates that connection between the two. That kind of confirms connecting the beam. You can have a rigid or flexible behavior with a rigid connection to that edge. It somewhat rigidizes that hole. You can also create a flexible connection there as deformable. That may be more of what you want to let this hole flex under load. With that, we have our beam connected to both sides of our shell. Let me go through our next connection opportunity. Here we have a fastener missing at this end of our fitting. So what I'd like to demonstrate here in our connection is the body-to-body beam. Essentially, this will automatically create a beam 180 for us and connect the ends to where we specify. So let me insert a beam. This beam, by default, has a circular cross-section. So this is one where it must be circular, whereas utilizing the line bodies and actual beam cross-sections, you can create whichever you like. In this case, let's create a titanium, again, a titanium alloy fastener, then put in our radius here, 0.0945 for our high lock diameter, and here's our body-to-body. So now we need to specify the selections. In this case, we'll scope to the front curve of the angle as our reference. And then if we zoom back out to the other side, let's say our mobile is the steel fitting. And once we've selected that, confirm that, you'll see that this beam is automatically displayed at the appropriate radius, and you can confirm that will fit into the hole. And so that is an automatic kind of beam and constraint equation attachment to the two sides of the shell, and that helps us visualize all of the connections. Again, with the beam connection, you can also utilize the rigid and/or flexible and deformable behavior at the attachments. And again, I'd tend towards using deformable to allow those shell elements to deform as they may under load. Okay, next, let's now, after setting up the problem, let me quickly highlight just some of the boundary conditions. Of fixed the ends of our angles at the very end, so that's a fixed, rigid displacement constraint. I've also applied a load, kind of a bearing load and an axial load on the lug. So we're trying to pull up and away from our lug. Let's go take a look now at looking at some results and some results specific for beam post-processing. So let me put that mechanical system away and bring up a solved system just for efficiency here. First thing I'd like to do with this is kind of show you one of the neat features when you do use beams and joint connections. In this solve system, once you highlight the solution information folder to start reviewing results, by default you're switched over to the worksheet tab to get some information about the solver output. If you switch over to the graphics tab, you can actually switch the display to display those finite element connections that are generated behind the scenes. And this is somewhat helpful to understand how are these connections being made. You may be using pinball radius to attach more of your nodes and elements. You can zoom in here that these beam elements are being kind of spidered out to the various holes and the various nodes. And sometimes that's helpful in understanding what's going on. You can also display these beam connections on the results as you're post-processing. So once you switch that over, if you look at an equivalent stress, you can review and post-process with these spiders on the post-processing. Okay, let's take a look. Let me turn that information. Let me turn the connections off while we're post-processing. Let's switch over now into looking at some stresses review. You may be interested in post-processing stresses in individual components. So you can see how the connections, typically you have some stress peaking in the first fastener of the load or joint connection. If you do turn on your thick shells and beams for air shell models, you can visualize stresses through the thickness, so it displays the shell through thickness bending, and that's a visualization tool. You can also, let me highlight a couple other post-processing tools specific for this type of fastener modeling. Here we have a beam tool that's available from the tools menu. The beam tool here will allow you to look at direct or axial stresses on the beam finite elements. It'll do the maximum bending stress and does some of the combined axial and stress post-processing. So that's a neat tool used with beam elements. For the joints we created with the automatic joint feature, you can utilize beam probes. What the beam probes will do is will allow you to kind of look at the load transfer. You can insert various beam probes for each beam connection that you use throughout the model, and then you can post-process those for either axial force or shearing force. And sometimes what I like to do is take our chart feature. The chart is available on that upper toolbar, and with the chart feature you're allowed to select multiple results quantities through the outline tree and assemble a chart. Once I do that, I have information from, in this case, all my various beam probes. I can post-process within mechanical here. I can copy and paste all of this data over to Excel. In this case, if I'm interested in a load transfer to Excel here, I can copy and paste the data and then plot the load transfer for the various fasteners in that row. In this case, I've got shearing load plotted versus the fastener number. So that's a neat way to take a look at load transfer through the joint. And the last thing I'd like to do is for a joint probe. In this case, we attach the beam to both the lug fitting and the angle angle fitting here. For joints that are inserted, we inserted a fixed joint to connect both ends of that beam. You can also include a joint probe to get those reaction results as well. So either fastener modeling method, you can extract those loads to get the load transfer in this global level modeling. One note here before we move on, this is just a kind of quick note here that this is kind of an upper level loads modeling procedure. In this example, I don't have any body-to-body contact. However, this is more or less just a linear model. However, if you're using shell elements, you can include body-to-body contact with the shell offset due to the thickness of each shell. At this point, I'd like to open in our webinar our first poll. And this is just to kind of get a little feedback from you. And what I'd like to do with this poll is to just kind of query what type of modeling procedures do you typically perform. In this question here, do you usually just use shell models and connect things with springs? Do you perhaps use shell models with the actual holes and use beams to tie them together? Do you have solid models, 3D solid models, and connect them with springs or beam elements? Or do you have 3D solid models with fasteners? So we'll give you a little bit of time to answer this. And let me put away this model and get our slides back before we move on. Okay, looks like many of you are answering. Let me give you a few more seconds here to participate, and then I will show the results here. Okay, we're closing in. Okay, now when we're compiling the responses here. Okay, let's share these poll results with you. We had a large number of people that are performing the 3D modeling. So it looks like a good portion of the group is performing 3D solid modeling, and many of you are connecting these models together with detailed solid fasteners, and some of you are using springs to connect them together. So looks like a good portion are modeling 3D bolted joints, so let's move on to that topic. In the next section here, we may have solid CAD parts that have detailed features, and we want to model a bolted joint with all the particular parts involved, and we may be performing a local submodel, or we may have a full joint and we have all the applied loads and connections in there. For this model, it's a larger type of problem, but we have a lot to set up, but it will provide lots of detailed information in terms of the part interaction, the mating surfaces, how they're performing, and the detailed stresses within the bolts and the native parts. You can model full 3D solid bolts with the threads and the shank and nut. However, that's not discussed here, and that's generally modeled with a submodel and a fairly fine resolution model. So let's move over to our next mechanical section here. In this example, I have our detail solid 3D steel fitting and fasteners here. We have the same loads and boundary conditions here. I've got my bodies colored by the material. Let's take a look at a couple meshing aspects. When you do go through meshing bolted joints in this fashion, there are some mesh techniques that are important. With meshing, I like to use a couple techniques, and one is the inflation option. Let me highlight just the upper angle here. In this upper angle, let me hide all the other bodies here. One of the mesh techniques in using the inflation layer allows you to create a refined mesh around the holes. In this particular mesh technique, you define the surface you're going to apply the inflation layer, and you specify the edge and get those elements radially emanating away from the edge. And so you can, with mesh constraints, you can get a large number of elements around the hole and have a nice mesh emanating away from the hole to capture those peak stresses, as well as perform some detailed contact setup so you can ensure contact between the holes and the fasteners. In addition to concerns with the hole mesh, you also want to ensure that your fasteners are meshed well, and for the same reasons, you want to have the mesh in the fasteners with enough detail in the elements just to ensure that contact can be set up properly between the shank and the hole in the native material or parent material, and then also with the head and the nut in contact with the angles. So those are some important things in paying attention to the mesh. The other important part of setting up these types of problems is setting up contact between all the bodies. By default, most people have in their setting in mechanical to initially have mechanical set up all the contact for you. I'm going to replicate here. I'm going to create a new connection group here and create automatic connections. And what mechanical does is takes a look at all the various bodies here and automatically sets up the contact for you. Okay, so let me take a look at this new contact setup. Here in this contact part here, let me take a look at all the contact regions here. You can see in this new contact setup, it did go through, evaluate all the surfaces via proximity between all the bodies. Generally, with these types of models, there's a large amount of contact set up for you. With this, you can rename all the contact pairs based on the attached parts. Hold on just a moment here. That sometimes is helpful in identifying, rename based on definition, identifying all the contact pairs that are set up for you, but quite often this is a lot to handle, and by default they're all bonded. One of the methods to tackle the contact between the parts is combining all the parts. So if it is automatically set up for you, if I know I have a number of different contact pairs that are in the same region and I want to combine those, for example, the lug fitting to all the upper angle fittings, I can select all of these automatically generated contact pairs. You can see that this is setting up the contact between the angle and the inner surface of the lug. Once those are highlighted, I can right-click and merge those selected contact regions. So this combines those into one single contact region, and then you can manage this, the multiple faces, through bonded contact, through frictional or frictionless contact. Quite often I'll use frictional contact with these types of problems because it sets up a little bit of force in between the joint once the contact is detected, and if you have rigid body motion issues, if you have parts that are floating in space, sometimes a little bit of friction will help resolve unconstrained parts or rigid body motion issues. The other thing is with this type of contact setup is a neat feature that most people have thought that was only available in setting up joints, and that is different ways to view contacts. Typically when you highlight a contact pair, it does kind of ghost out all the parts that are not involved in the contact pair and sets up the blue target surface and the red contact surface. In the upper toolbar under body views, this sets up kind of a triple window system here that allows you to automatically highlight only the contact body and surface and only the target body and surface. So with the sync views option, as I turn the model, it allows me to review, okay, this is in fact the contact surface I'm after, and this is the target surface I'm after, because it's quite challenging with the surfaces overlapping each other and making sure you set those up properly. And so through the contact body and target view, that'll help you set those up properly. Unsyncing those just allows you to rotate each window individually. I'm going to delete this particular contact group. We have that all set up already. Actually, let me just hide that. In this particular contact pair, we have multiple contacts already set up. One thing I also like to do is set up our contact scoping via name selections. Usually, many folks will select portions of the geometry to set up contact. I'm going to set up a new contact pair. Let me set up a frictional contact pair. And in this particular example, let me shut off the body views momentarily. I'm going to set up a contact pair between the fastener shank and the various angles. In this contact pair, I'm going to use my predetermined name selections. If I go down to the name selection here, you can see that I've set up, based on when I imported the geometry, a number of name selections. Here I've got upper fasteners shank here, and let me highlight these particular parts here. So there's all of our fasteners. If I highlight the name selection, upper fastener shank, you could see there's all the contacts of all the contact surfaces have automatically assembled into one name selection, and that's a surface. You can see the 32 faces, and the corresponding mating side to these shanks would be the holes in the native material. So let me go in and highlight our native or parent material parts, highlight all the other, or hide all the other bodies, and with these particular parts I've set up angle upper and angle upper, the upper holes here I've got set up, and these are both, you can cross multiple bodies, and these are the hole surfaces both in the angle and in the steel fitting. So once you've set that up through name selections, making your contact pair setup is quite a bit easier. So in the new contact pair, when I scoot up to our new contact pair, I can select the contact side as our upper fasteners in the shank. Actually, this is scope to geometry selection. Let me switch over to name selection. That way now it's just a pull down, and I can use the upper fastener shank and then select the upper holes, name selection, and immediately everything is selected automatically. So let me show all the bodies here, and now I have both the contact body view and the target. So this is a great way to set up contact between the various parts of your fastener. So you'll need to set up the shank, fastener shank, you'll need to set up the head to surface and the tail to surface contact. Some of the things I recommend in the contact setup between the fasteners is going through the details of the contact pair. I will typically use some form of friction that may be important. I will also somewhat use asymmetric behavior to to kind of control the amount of contact that gets set up. You'll also see down below in the advanced the interface treatment. Interface treatment by default will use whatever geometrical gap or penetration, and it'll have to resolve that between the contact and surface. So sometimes if you want to just start off your contact pair as completely touching, so that the surface and contact and target surfaces are touching, this will mathematically adjust that independent of the gap and or penetration. This is very handy in getting contact problems to start to converge properly. Some of the other things I'll control in the details of the contact pair is manual controlling of the stiffness. If you're using a penalty-based contact method, you can adjust the stiffness factor down below. Let me move on to, that's our connections. We'll review some of those results when we took a look at joint and finite element model results. Before we do that, let me just emphasize bolt pretension. In this example, you can see down below here in our static structural example, I've got a number of bolt pretensions set up. This is important for preloading bolts. It's very important for understanding load transfer through the joint. And that we can do this, I've got one bolt. If I highlight this, I've got a number of bolt pretensions set up. Let me set up another one for you just to go through the details. When we set up bolt pretension, there's a couple different methods. Let me go back in and just show one fastener here. Let me hide all the other bodies. Oops, let me hide all other bodies. When we set up bolt pretension, we can do it via two methods. Bolt pretension is under loads, and when we do this, there's two methods of setting this up. We can set this up via assigning it to a surface or assigning it to a body. And this is automatically taken care of by the geometry you've selected. So let's say you have a bolt and you select a cylindrical surface. Mechanical detects a cylindrical surface that is applied and scoped to this bolt pretension. It'll automatically understand the centroid of that cylindrical surface, the body. It'll split the body mesh and start enforcing that preload. Most often, sometimes when we import bodies, or in this case I've got a bolt divided up into multiple bodies for meshing purposes, so we need another method to apply the bolt pretension. You can accomplish this by selecting all the various bodies that you'd like to assign the bolt pretension to. In this case I've got 4 bodies in the shank. Actually I've got the 8 bodies through the center as well. And once I select those 8 bodies, let me go into box select. Once I've got those bodies selected and I apply, the details switch over to looking for a coordinate system assignment. So with these bodies assigned to the bolt pretension, I have a coordinate system defined as a fastener 1 coordinate system, and basically this will define the XY plane to split the bolt shank, to start enforcing the preload between the split mesh, and then the Z direction of this coordinate system will define the direction of the preload. And you can specify the preload down below in the details. Also, I've got a number of bolt pretension set up here. Let me display all the bodies here. With bolt pretension number 6, so you've got a number. You can individually control each pretension. If you have different types of fasteners, you can load each one individually, and that can be handy. The next item I want to really emphasize is when you do have mechanically fastened joint setup, you do want to perform a multi-load step analysis. And with this type of analysis, you can control this under analysis settings, and the purpose for this is to set all the preloads in the first load step and then apply your mechanical load in the second load step. So if we switch this number of load steps over to 2, this automatically assigns 2 load steps for all the loads. You'll see our fixed supports stay put. If we assign, let's say we assign a pressure, or actually let me delete the pressure. Let me go back in under loads and let's say we assign a bearing load in our lug here. You'll see once we apply that bearing load, let's make some components in the X and Y. You'll see over in the tabular data portion, 2 available load steps: when to apply the load and when to keep this at 0. So in the first load step, I'm going to apply this as 0. And in the second load step, I can switch this over to our load, because I'm using the first load step to apply all the bolt pretension. One thing in this bolt pretension we just set up, you'll see it's automatically set to load in each load step. What we want to do is switch this over for the second load step to lock this in place. So you click on the load icon, click on lock, and that will automatically lock this in place. That's important because the iteration to resolve the preload is already taken care of, so you want to lock the 2 halves of the bolt in place, and we can monitor the bolt pretension later on in the results post-processing. Okay, that's some of the specifics for bolt pretension and bolted joint setup. What I'd like to now do is kind of cover a new poll. In this particular poll, I'd like to kind of query on what type of, if you are doing detail stress analysis, how much detail and results you're after. So let's open up this poll. In terms of results post-processing, in these assemblies, are you interested in just looking at the load in each fastener, maybe even in a 3D scenario, or and using a handbook calc to determine the underlying stresses? Or are you interested in, hey, I know I just need a net section stress in the parent material because I know the KT and I'm going to do a fatigue analysis? Or is it most important to you that you get the detail stresses in all the parts? Is it the detail stresses in the parent material or the fastener itself? So what type of information is most important to you? Okay, looks like we're getting there. Let me give you a few more seconds to submit your answers. Looks like a number of us are kind of focusing in our detail 3D stress. All right. Okay, let me close out the poll here. I'm going to share the results from you, from your submissions. And while that's compiling, let me put away our pre-processing demo and bring up some results to look at. Okay. Taking a look at our poll results, looks like most of you, over 50% of you, need to know those detail stresses. So let me cover that in the next portion of this webinar. Detail stresses, looks like some of you are interested in fastener loads and so forth. In this 3D scenario, there's a bunch of information to post-process. A lot of this you'll post-process as you typically would in looking at detail 3D stresses. For example, if you have looking at maximum stresses in the upper angle, take a look at scoping those results to individual bodies. You get the automatic scaling of the legend here, so we can look at the peak stresses. You can look at stresses through the thickness. So many of the techniques you do for regular post-processing are effective for looking at stresses in the individual part. One thing you want to do with the multiple load step analysis is keep check on the substep, or I'm sorry, the load step you are post-processing. That's identified in the time item in the legend, and you can select which display you'd like to show by selecting the individual time point in the tabular data. Next important information when post-processing bolted joints is understanding the contact and the load transfer. With that, you can look at insert a contact tool from the solution toolbar, come down to contact tool. I like to scope individual contact pairs and look at the individual results for specific pairs. It's just a way to organize the results. First thing we typically look at is contact status. Where has contact been detected? where do you have sliding contact, and because of friction defined, where do you have sticking contact? So we can see here that we've got some sticking. The clamp up of the bolt is providing some sticking. We have some shear load transfer through this particular joint. You can look at pressure, and you can look at frictional stresses for these types of load transfer. Also important in post-processing is the contact pairs with the particular fasteners. So we want to take a look at the status of those, look at the bolt clamp up. In this case, you can see, looking at just the contact pairs of the fasteners, you can see the orange indicates contact's been detected. We have sticking contact between the head and the parent material. And also what's interesting, you should see the method of load transfer here allows you to look at the kind of the through thickness contact on the shank of the bolt. In this case, we've got the steel fitting thickness bearing up against here, and you have the aluminum angle bearing up against the top of this fastener. So that's a clear indication you kind of have a beam in a socket action where you have through thickness bending of the fastener itself, and that's kind of confirmed by looking at the pressure profiles, and you can evaluate the penetration of your contact as well. Some other things you could look at is, in terms of post-processing, is assigning bolt pretension. That allows you, in the solution for probe, you want to look at bolt pretension, and this lets you monitor an assigned 100-pound preload. You can look at how that preload is affected by the mechanical loading in the subsequent load step. So that allows you to monitor. If you have one more moment, I'd like to just cover another example here. In an additional model, what I did was included some advanced features of contact, and that is assigning, in these particular contact pairs, assigning different interface treatments. Let me switch off the body views. Instead of adjusting to touch in the particular fasteners, if you have an interference fit fastener, or maybe you have a hole that's been bored out too large, you can adjust that through the interface treatment through a negative offset or a positive offset. The positive offset will increase the penetrations. The negative offset will essentially loosen up the holes. And if you go through, include some of the post-processing of those, we can look at the stresses. In this case, I've included a large number of, I included interference fit in this particular fastener. You can review the effects of that, and you can also review the effects of a loose fastener in this 3D concept. Perhaps you have some load peaking in that first fastener hole, and this is the loose fastener here, and not as much load transfer through there. And so those are some neat features in using the advanced contact setup to kind of evaluate various conditions in the bolted joint. Okay, I've covered a lot. I've gone over a little bit. I appreciate the time you spent with us. I do have a few questions via the chat mode. I'll address those and answer those. What I'd like to do now is just conclude our webinar for detailed bolted joint modeling, covering a couple different approaches. And what we covered today was some of the key features using use of joints with fasteners in 2D models, using some of the visualization tools and the beam connections, also using meshed beams, or those line bodies meshed with beam finite elements as fasteners. We covered some part-to-part contact setup with friction, looking at the interference, the interface treatment, covered bolt pretension, and a multi-load step analysis, and some specific results post-processing with bolted joints. And so with that, I would like to conclude this webinar. I appreciate your attendance, and I hope this has been valuable for you. And thank you for attending.